Hello my dear students, I welcome you to the NeetWorld. So today in this particular video we are going to discuss about the important concepts for NEET, JEE and also for EAP set. So today's topic is chemical bonding and molecular structure. This is high weightage topic for all the competitive exams for 11th and 12th students. So you have to watch this complete video and it will be definitely helpful for you for your preparation. Okay, so in this particular video we are going to see what exactly the chemical bond and its type. And then next, what are the approaches given by the different like scientists or chemists, we can say, to explain this like chemical bond. Okay, so it means like what exactly valency bond theory and what is exactly hybridization concept and valency shell electron pair repulsion theory. Okay, so here let us start our topic. What is exactly chemical bond? It's a force of attraction between the atoms which holds the two atoms together. For example, we have two atoms, let us say atom 1 and atom 2, which are existing individually, and there is some kind of force which holds these two atoms together to form a molecule between them. Okay, there is a bond formation between them or some kind of force which will hold these two atoms together to form a molecule. Okay, so here what is the reason to hold them together? What kind of forces it may exist? See here we are saying force of attraction. So what kind of forces it may have? So what is the reason behind that force? So that's why we have a question here. Why chemical bond formation takes place? Okay. So we know in the nature everything happens to attain the stability, right? Okay. We also do things to attain our stability, our stabilized goals, right? Okay. So here in order to attain stability, chemical bond formation takes place. So how this chemical bond, like how the compounds or the atoms will attain the stability. Let us look into it. So we know in the periodic table we have 18 groups, right? So the last group, 18th group, we are saying it as inert gases or noble gas elements, right? So all the elements will always tends to attain that noble gas configuration or inert gas configuration, which is highly stable. So that is the reason I have mentioned here the bond formation is associated with the stability. So between the atoms, the bond formation is associated with the stability. So an element will attain the stability by occupying inert gas configuration, okay, which is considered to be stable. Okay, so this noble gas configuration, depending upon the element to element in the periodic table, this noble gas configuration can be attained in different ways. For example, if you are looking for the alkali metals, what are the alkali metals? The first group elements like lithium, and the next sodium, the next potassium, rubidium, cesium, all these elements attain the noble gas configuration by losing one electron. Okay, because let us take this sodium element which is having atomic number 11. So what is the electronic configuration it has? It is having like 1s2, 2s2, 2p6, 3s1, right? So there are 11 electrons in the its electronic configuration. Now, if you look at this, it will be having this 10 electrons, which means it is a nearest noble gas configuration. That is what? Neon electronic configuration. So, by losing this 1s electron of sodium, like from 3s orbital, it will attain noble gas configuration. That is what? Neon gas configuration, and that will be highly stable. So, alkali metals, generally metals loses electron to attain their noble gas configuration. Okay, so here first thing is by transfer of electrons. So now, for example, let us say we have a metal like sodium and we have a non-metal like chlorine. Okay, so now halogens, the 17th group elements, what is the electronic configuration they have? Like general electronic configuration, we can write it as NS2 NP5, right? And for this it is NS1 electronic configuration will be there. That is what I am saying here. Okay, so now by losing this electron like noble gas, here we have helium, like not helium, it is neon. The next 3s, the next what we have here 3s1. So by losing this electron from the sodium, it will become what? Na plus, and one electron is released from here, right? So this electron can be taken by the sodium and like chlorine, it will become what? Now Cl minus. Now electronic configuration, this NS2 NP5 becomes what? NS2 NP6. Now it is also attaining noble gas configuration. So some elements will give the electron and some element will accept the electrons. So here that is what the transfer of electron taking place. So between a metal and non-metal, always ionic bond formation takes place. So this is a general statement we can give for the metals and non-metals. So between metal and non-metal, ionic bond formation takes place by transfer of electron. Example you can take NaCl formation. Okay, so we will discuss about that in detail after some time. Okay, then next we can look into mutual sharing of electron. For example, let us take two halogen atoms. So if I say chlorine atoms itself, so what is the electronic configuration we have for chlorine? It will be, just now we have written, for noble gases it will be NS, like for halogens it will be NS2 NP5. So how many valence electrons? There are 7 valence electrons now. So it means we have one odd electron. So let us consider those electrons like this. I will explain how we are drawing this structure. In the Lewis dot structure we will be going to see. So these 7 electrons, here I have kept them like a dots. Okay, each dot represent 1 electron. Okay, like this you can consider for both chlorine atoms. See, so here we have 7 electrons. In order to fulfill their octet, it means in order to get nearest noble gas configuration, they tends to like accept an electron, or they tends to share the electron with the similar elements. So here this chlorine also required 1 electron and this is also required 1 electron. So each will mutually share the electron. Therefore now for each chlorine we can consider them. They have, see how many electrons are there now. For this chlorine it will be 8 electrons. See, this is a mutually shared electrons. The bond which we are showing, that electron belong to both atoms, we can say it as mutually shared electron, and it is a sigma bond here. So how many electrons are there? 1 2 3 4 5 6 7 8. Similarly for this chlorine also. So mutually sharing of electrons will result to form covalent bond. What bond it is? Covalent bond. The bond formed by mutual sharing of electrons is called as covalent bond. I hope it is also clear. So sometimes the formation of bond takes place by donation of lone pair of electrons. Okay, we will be seeing this later. Okay, so what type of bonds we have? So first one, just now we have discussed about ionic bond, and it is also called as electrovalent bond. What is that? Electrovalent bond. And the next one we discussed just now, covalent bond, which is formed by mutual sharing of electron. The third one is coordinate covalent bond. So in which third example we have discussed now, sometimes let us say NH3 we have. So here it is having one pair of electrons. Now let us say there is another compound BF3. Let us consider here we have an empty orbital. So to this empty orbital, whatever the lone pair present on this nitrogen of ammonia will be donated. Therefore it results to form NH3 and BF3. So something like this we can write. This bond, whatever the bond here we are representing, is called coordinate covalent bond. So this is the simplest way we can discuss about coordinate covalent bond. Okay, next thing is what we have here, the next metallic bond. So this can be explained using like electron C model for the metals. Okay, it will be seen in the metals only. Okay, hydrogen bond, this is a special type of bond which is relatively weaker when compared with the first 4. These two are relatively weaker when compared with the first 4 bonds. Okay, so we will discuss separately about these 2 bonds, like van der Waals bonds and next hydrogen bond. Okay, the next, so in order to explain like how these bonds are formed, like we have different approaches. The first approach is Lewis dot structure. Okay, so Lewis dot structure, he explained that for whatever the elements he has taken, so he has considered the valency electronic configuration. For example, if you are considering for hydrogen, what is the electronic configuration? We have hydrogen atomic number is 1. So we can directly write 1s1. For helium it will be 1s2. So he has represented that whatever the valency electrons are there as a dots on each of that element. For example, let us say carbon, we have carbon atomic number is 6. So we can write the electronic configuration as 1s1, 1s2, 2s2, 2p2. So like this we can write the electronic configuration, right? Now valency electronic configuration means consider the outermost shell electrons. See, outermost shell is like n value should be highest one. So it will be 2s and 2p. This belongs to outermost valency electrons, right? Outermost shell electrons. So how many valency electrons are there? No, there are 4 valency electrons in carbon. So these 4 electrons, I am not saying this inner electrons, I am saying only the outermost orbital electrons only, outermost shell electrons only. Now consider them as like a dot of each electron as a dot around the carbon like this. Okay, now this is how he has represented for carbon. Similarly for nitrogen, what is electronic configuration? Valence electronic configuration, it is 2s2 2p3. So therefore 2s orbital, 2s electron, like 2s2 2p3. Therefore how many electrons are there? 5 electrons are there. So 5 dots are represented. Similarly for all the elements you can consider. I hope this is also clear. So let us move further to understand it more clearly. Okay, so now what he told is, so for example, for formation of methane, let us consider we have a carbon atom. I think it is clearly visible only. Okay, I will try to write it again. So here we have a carbon atom. Just now I told you for formation of methane, we know central atom is carbon over here. So let us consider carbon like this. Now how many valence electrons are there around the carbon? Just now we have seen it is 4 electrons, right? And for hydrogen, I already discussed, it will be 1 electron. Like that 4 hydrogens are there now. So you can just keep 4 hydrogens, each one with 1 electron as a dot. Okay, now if you are looking into it, so here you can make a bond. See, this electron and this electron will pair up to form a bond. Therefore just look here. Therefore after forming these bonds, how many electrons are there around the carbon now? See, by sharing of these 2 electrons between the 2 atoms, we got a pair of electrons here. So how many pairs are there? 1 2 3 4. So 4 pairs are there. 4 to the 8 electrons. Now carbon attained its nearest noble gas configuration, that is what? Neon gas configuration. Now the carbon will be stable. Similarly hydrogen got 2 electrons, that is what? Duplet configuration, we can say helium gas configuration. Therefore carbon and hydrogen is stabilized here. Okay, so I hope it is clear how to draw Lewis dot structure. Okay, so now according to Lewis, only those compounds will be stable which follow octet configuration or octet rule. So if the element is having 8 electrons around it, that is considered as octet configuration. So those elements which is attaining that 8 electrons after forming a compound or a molecule, that will be considered to be stable according to Lewis. But there are few exceptional cases in which the compounds are existing even though they are not following the octet rule. Okay, let us see. So let us consider, so this can be considered as limitations of octet rule. So what is the first octet rule here? I mean limitation for the octet rule. Look here, incomplete octet of central atom, there are some compounds. See, what is the first like limitation we can say? Incomplete of octet of the central atom. So let us see here, there are some compounds. What are those compounds? Let us say BF3 I am taking. So the central atom here is boron. So what is the atomic number for boron? It is 5. So what is the electronic configuration for boron? Atomic number is 5. So you can write it as 1s2, 2s2, 2p1, right? So how many valency electrons are there? 3. I already told you, you have to consider only valency electrons. Now consider them as a dots around the boron atom. Okay. Now how many surrounding atoms are there? Fluorine are 3. So we know fluorine atom require 1 electron because it is halogen. So by accepting 1 electron or by pairing with 1 electron, it will become noble gas configuration. That is what here I am representing. For each fluorine we have 7 electrons. So here also you can write 7 electrons, right? Okay, here also you can write 7 electrons. Okay, I hope you got how I am writing this. Okay, so now let us pair up this electron here, here and here. Now if you are looking into it, so just look here, for each fluorine we are seeing here 8 electrons are there for each fluorine. See, 1 2 3 4 5 6 7 8. So all fluorines are happy now because they are getting their nearest noble gas configuration, right? Now what about central atom boron? See here how many electrons are there? 1 2 3 4 5 6. Only 6 electrons are there. It is not following octet rule. It means according to Lewis, it should not be stable or it should not be exist. But this molecule is existing, which he was unable to explain the reason behind this. So we can consider it as what? It is a limitation for his rule. So here we have a one like empty orbital. We will discuss about this empty orbital in the next class. Okay. So the next, this is the one example we can say. So all 13th group elements, what are the 13th group elements like boron family elements will form trihalides. I mean whatever the trihalides exist, those will be considered as example for this incomplete octet of central atom. Okay. The next, there are some compounds which are having expanded octet. It means these elements are having electrons more than 8. It means it is more than octet rule, right? So here it is lesser than octet. Second one is more than octet. So let us take the example as PCl5. This is the example for second statement which I have written over here. Okay. Some elements in third period have more electrons than 8 in the valency. For example, here like SF6 we have PCl5. So let us look into it how it will be. See, phosphorus we have, it is 15th group element, therefore it has how many valence electrons? 5, right? So you can write 5 valence electrons like this. Now how many surrounding atoms are there? 5. So put each chlorine around the like this, just for our understanding you can keep it like this. Just like this you can write. So now see how many electrons are for each chlorine. It is satisfied with the noble gas configuration, but the central phosphorus is having 10 electrons instead of 8. Therefore we can consider it as expanded octet, which is not explained by like Lewis dot structure. So this is also one limitation. Okay, so we will be discussing about PCl5 and exactly what structure it has in the upcoming slides or in the upcoming classes. Okay. So this is also one of the limitation. You can also consider for SF6 also. Then next, see xenon, which is a noble gas but still forming some compounds. So what he told, all the elements attain noble gas configuration because all of them are having less stability when compared with the noble gases. Therefore here according to him, xenon should not react with any of the elements. It should, because it is a stable noble gas, right? But it is showing some reactivity which was not explained by him. Therefore it is also considered as limitation for his explanation. Then next, Lewis dot structure or Lewis dot octet rule give no idea about the structure. See, I have written the random structure for phosphorus, I mean PCl5, and also for BF3. So these are the not accurate structures or exact structures of this particular compounds. So this was not explained by, the exact structures was not explained by Lewis dot like octet rule. Okay, therefore these are the 4 limitations you can consider. I hope it is clear. If you have any doubts you can ask me in the comment section. Okay, then next, give me the answer for this question. We already discussed exactly what answer here, because in the previous example only I have explained. Just read the question. Which of the following compound has expanded octet of the central atom? So by looking itself we can say, see, just now I explained PCl5 will be having expanded octet and SF6 will be having expanded octet. Just count, if the electrons around the central atom is more than 8, then that is considered to be expanded octet. Okay, therefore option 2. Okay, and this will be having incomplete octet. First one is having incomplete octet, like this you can consider. So this will be having how many electrons? So you just count and consider the answer. So I hope you got how I am saying PCl5 here. Now we have seen the basic version, that is what Lewis dot structure. Let us go into the types of bonds. We have the first one is ionic bond. Let us consider. So here this ionic bond is formed by complete transfer of electron, generally from a metal to a non-metal. Okay, from a metal to a non-metal. The resultant compound, for example here again I am taking sodium only. Sodium loses 1 electron and become Na plus 1 electron is released from it, and now this electron, so whatever the electron I am writing, see for chlorine for halogens, we know one electron is less. Therefore, this electron will be taken by the chlorine atom and it will become chloride ion. Therefore, see, this is having cation and like positive charge, and it is an anion which is negative charge. So there will be some electrostatic force of attraction between the two oppositely charged ions, which results to form ionic compound. We can write it as NaCl. Okay. So what is the reason for the like compound formation? It is electrostatic force of attraction between two oppositely charged ions. Okay. Okay. So what are the factors affecting in the formation of these ionic compounds? The first factor is ionization energy. Okay. So what is mean by ionization energy? See, sodium is becoming from atom to it is becoming ion. So this conversion, if you are taking it in the gaseous state, so this conversion is called as what? Ionization energy. So this is the one factor. Then next, electron affinity. See, chlorine atom is accepting one electron. See, it is accepting one electron. Let us take it is in the gaseous state again. Now this process is called electron affinity or electron gain enthalpy. The energy associated it is considered to be electron gain enthalpy. Okay. And the next one is lattice energy. So these are the three factors which are affecting on the ionic compound formation. Okay. So how it is taking again? So see here, for sodium atom, how many electrons are there? It has atomic number. Sodium is having atomic number 11. Therefore, consider this is the nucleus of sodium atom. This pink color one is the nucleus of sodium atom. So here around the nucleus we have 2 electrons in 1s orbital and 8 electrons in the 2s orbital. That is what 2s2 and 2p, 6, 8 electrons are there, and we have one more electron, that is what 3s1. So here I have highlighted as 3s1. So now this electron is lost from the sodium and it is gained by, see, and it is gained by this chlorine, which is I am highlighting with the green color. So this will be gained by this chlorine. Therefore, it is becoming now 8 electrons in its octet, I mean in its valency, and this is becoming the nearest noble gas configuration. Therefore, the resultant ions will have some electrostatic force of attraction between them and results to form ionic crystal. Okay, I hope it is clear. Now, what are the characteristics of these ionic compounds? See, ionic compounds, like, see, consider that the small one which is in pink color, consider it as cation, Na plus, or any cation you can say, not always Na plus only, any cation. And now this can be considered as anion, which is having larger in size. Okay. Now see, cation, anion are arranged in a proper orientation in the crystal lattice, right? This is the lattice you can consider. Now, due to this proper orientation of cation and anion, so they have hard, brittle, and they are crystalline formation. So this lattice, if you see, all the atoms are properly oriented, which will result to form a crystalline like structure. Okay, crystalline formation. Okay. So generally ionic compounds are considered to be hard and they have brittleness. Okay, and they show high melting and boiling points. Okay, they are polar in nature. Since they have cation and anion poles like ions, we can consider it as polar in nature. So next, since it is polar, we know polar compounds will soluble only in polar solvents. Therefore, what are the polar solvents? Let us say water is a polar solvent. So we know, let us say some salt you can take and keep it in the water. It will dissolve, right? So we can say polar compounds will soluble in like dissolves like, we know, right? It means polar will dissolve in polar solvent. So therefore you can interlink here. They soluble in polar solvents such as water and insoluble in non-polar solvent. If we dissolve the salt in like in petrol or any non-polar solvent, organic solvent, it will not get dissolved, right? So we can take it as an example. Okay, then next, okay, these are good conductors of electricity in their fused state or molten state, we can say, or in their aqueous form. Or aqueous form we can also consider as solution. Okay, why it is? Because the mobility of cation and anion are there, mobility of ions are the reason for the conductivity in the like fused state or in the aqueous solution form. Okay, and they are bad conductors in the like solid form, in like bad conductor of electricity in the solid state, because ions are unable to move. See, they are closely packed, ions are closely packed, there is no movement of ions in the solid state, like solid form. Therefore, it is a bad conductor in the solid form. Okay. Okay. Next, that is about ionic bond formation, and now let us discuss about covalent bond. So what exactly covalent bond? Okay, so here the gain, or already we discussed at the beginning in the intro part. Let us look into it once again. The gain or loss of electron cannot take place between the similar elements. Similar elements means, for example, like elements belongs to a particular group. Let us say halogens only, or you can take hydrogen family, or like hydrogen atom also. Okay, so now here hydrogen also required one electron in order to like fulfill its 1s orbital, like it has 1s1 electron. It required one more electron to get its doublet configuration, and for a chlorine we know it has 7 electrons around it. It also required one more electron to gain noble gas configuration. Therefore these electrons are mutually shared between these two atoms, results to form a covalent bond like this. So similarly, if we take two chlorine atoms, so now see, it is also having 7 and 7. Therefore if they share this, mutually share the one electron of both, they will be getting 8 electrons, which is stable electronic configuration. Okay, I hope this is clear how this like covalent bond is formed. Okay, sometimes let us say oxygen is there, sometimes multiple bond formation also takes place. So let us say two oxygen atoms are there. So here what is the valence electronic configuration for oxygen atom? It is 2s2 2p4, right? Okay, so it means 6 electrons are there. So let us put that 6 electrons as dots as of now by following Lewis dot structure. Okay. So now here it has 6 electrons. This oxygen atom also has 6 electrons. So it means how many electrons are needed in order to get noble gas configuration? 2 more are required, no? So if they share these electrons, what happens? It will be also getting 8 electrons. See here, it will be also getting 8 electrons. Count these electrons, yellow colored one. So it will be 8 electrons for this oxygen atom. Similarly, count for this one also, the another oxygen atom. 4, 5, 6, these are mutually shared. Therefore we have to count for both the elements, 8 electrons. So both are getting noble gas configurations, right? So like this we have multiple bonds also in some cases. Both are covalent bonds only. Okay. So now what we need to study is, there is covalent character in ionic bonds. Just now we have studied about ionic compounds, then we have discussed about covalent bonds. Okay. Now we will discuss few more things about covalent compounds here. Okay. So this is also important topic. Okay. So covalent character in ionic bonds. So I just wanted to tell you that there is no there is no ionic compound which is perfectly ionic, like 100% ionic. See, once again I am saying there is no 100% ionic character for a particular compound. There will be at least some amount of covalent character in that compound. For example, NaCl is a ionic compound, but it is not 100% ionic. I hope it is clear. There exists some amount of covalency, okay, or covalent character. Okay, so we will see why exactly happening like that. Okay, see here. Here we have sodium atom. It is losing one electron and it is becoming what? See, this sodium atom. Let me take this yellow color. This sodium atom losing one electron and becoming sodium cation, like Na plus we are writing now. See this Na plus we are writing here, which we have highlighted here. Okay, now that electron is accepted by chlorine and it is becoming Cl minus, right? Okay, so now what are the ions we have? One is cation with Na plus and another one anion with Cl minus. Now this cation which is having positive charge, please look here very carefully. We have a positive charge on a cation, like let us consider this is a sodium atom which is having positive charge. Okay, and we have anion. Okay, let us write like this, and this is of negative charge. Okay, this is cation, this is anion, let us consider. Now see, anyway, this chlorine atom, like chlorine ion, here we have chlorine ion, in the center we have like nucleus, so around we have electron cloud, right? This electron cloud. Now this electron cloud of chlorine will be attracted by, chlorine atom is attracted by its nucleus And also here we have a positive charge on the, like more positive charge on this sodium ion, right? Therefore, the electron cloud, whatever the electron cloud of this chlorine is there, that is polarized by, that is like dragged itself by or polarized by this positively charged cation. Therefore, what happens? Whatever the electron cloud around the chlorine is there, that will be dragging towards the positively charged sodium atom, and it will be resulting something like this. See here, some of this electron cloud is like pulled towards what? Sodium cation. Therefore, see there is a like small amount of like electron cloud is shared between the two atoms, right? Therefore, this results to have some covalent character for each ionic compound. I hope this is clear. Okay, so now we need to like examine like which particular compounds will be having more covalent character and which is having less covalent character for a particular ionic compound. So in order to explain that, we have Poisson's rules to be followed to get the answer for those kind of questions. Okay, I will show you what exactly the Poisson's rule here. Okay, so covalent nature in ionic compounds are explained by Poisson, like Poisson's rules. So what he told is, again let us take cation, and here let us take this is anion. See, I am writing positive charge only, but this positive charge indicates what? The nucleus of anion. What that positive charge indicates? The nucleus of anion. And here this smaller size one always considered as cation for better understanding. Okay, now see, this like bigger size indicates the electron cloud is spread more extent because of its more electron density. Now these electrons are polarized by what? The nucleus of this particular element itself, and also neighboring positive charge, that is what? The cation. Okay, so now what happens? So the covalent for this particular, like covalent character for this particular compound will be more when this electron cloud is pulled very efficiently or very strongly towards this cation. So when it is possible to drag this like electron cloud towards this cation, when a cation is having small size, it means if the size is small, therefore its effective nuclear charge will be more, and it will be effectively drag the electron cloud of anion towards itself. This results to form more covalent character. I hope it is clear. See, it should contain small size, cation should contain small size, therefore it will be having more polarizing power. Okay, you have to check the polarizing power of cation and polarizability of anion. There are two terms I am saying. One is polarizing power of cation and another one is polarizability of anion. Okay, first point, in order to show more polarizing power, the cation should contain smaller size. In the short form I am writing pp of cation. So for pp of cation, it should be have smaller cationic size or more positive charge. See, if it is contain more positive charge on this cation, so this will be effectively drag the negatively charged electron cloud. Now it means electrons are negatively charged, we know, that will be like pulled towards itself more effectively when it is having more positive charge. I hope these are clear. These 2 points are clear. Now what about anion? Now we have discussed in point of the cation part. Now let us discuss about the anion. So now in order to push these electrons or drag towards the cell, see, the size should be very large. If the anion size is very large, what happens? That electron cloud, whatever the electron cloud around this like this nucleus, the anion nucleus, that will be easily taken by the cation, right? Therefore the electron cloud should be bigger or large in size. It means anion size should be large. The size of anion should be large. In another term, we can also say if there is more negative charge on the anion, so that will be easily polarized by this cation, or that will be easily dragged towards cation, right? Therefore this is also results to form more covalent nature. I hope this is also clear. Okay, so once again, cation should be smaller in size. What I am saying, cation should be smaller in size and cation should have more positive charge. And the next point is, third one is, anion should be large in size and more negative charge. I hope these 4 points are clear. Okay, so I think these first 4 points are clear, and the next this polarizability. This is about anion. 3 and 4 are about anion. Again, about cation, we have one more point. See, some elements are there. So, for example, let us say sodium cation I have and copper cation I have. So, both are cations only. Now, which will be having more polarizing power? Which cation will polarize this negatively charged electron cloud effectively? It means, see, the one which is the cation which is having pseudo inert gas configuration. What is mean by pseudo inert gas configuration? The elements, there are some elements like D block elements if we consider, it will be having 18 electrons in its valency. So those electronic configuration is considered as pseudo inert gas configuration. If we consider for sodium, it will be having only 8 electrons. That is what normal inert gas configuration. So in these two cases, the one which is having pseudo inert gas configuration, that is what 18 electrons in the valency, that will be having more polarizing power. It means if I consider NaCl and CuCl, see, anions are same but cations are different here, AB let us say. Okay, so which cation is having more tendency to drag the negative charge of this chloride ion? See, in both cases anion is chloride ion only, but cations are different. In one case it is cation is sodium ion, in another case it is copper plus copper ion. So now I am saying that this is having pseudo inert gas configuration, therefore it will drag this electron cloud more effectively than the sodium, therefore this compound B will be having more covalent nature. Which is having more covalent nature? Copper chloride, like CuCl is having more covalent nature than the NaCl. I hope this is clear. So now let us look into these first 4 points with some examples. Okay. Okay. So now, okay, sorry. Okay. So now let us say second group halides. What are the second group? I mean calcium halides. Let us say calcium fluoride we have. The next calcium like chloride we have, calcium bromide we have, calcium iodide we have. So these are the halides I am taking. So in all these cases cation is same. What is the cation here? In all the cases cation is chloride like calcium plus 2 only. So we cannot decide which is having more covalent nature, which is having less covalent nature, right, with respect to cation. But with respect to anion here, so anion is F minus, here it is Cl minus, here it is Br minus, and here it is iodide ion. So now we know these ions are halogens. We know like what are the halogen atoms in the periodic table? Br and I. Let us say these are the 4 elements we have. Now down the group, what happens to the size of the halogens increases. Now which anion is larger like large in size? So iodide will be having larger size when we compare with the fluoride, the next bromide. So which is having larger size? Iodide. So now we know larger anion will be having like more polarizability, therefore the resulting compound will be more covalent. So which is more covalent here? So CaI2 will be having more covalent character. I hope this is clear how we are solving this kind of questions. Now here I have mentioned on moving from CaF2 to CaI2, melting point decreases. Why it is happened? See, we just now we have studied ionic compounds have more boiling point and melting point. So here ionic nature, what happens from here to here? Ionic nature is decreasing, covalent nature is increasing. From here to here, what happens? Ionic nature decreasing and covalent nature increasing. It means the one which is having more covalent like more ionic character will be having more melting and boiling point. So Here I am writing covalent, more covalent character, less melting point. So based on this statement, which is having less melting point now? So see here, which is having more covalent nature, that will be having less melting point. Therefore, from here to here, what happens? Melting point decreases. This is the order for covalent nature. So, but here I mentioned about application. That is what melting point application. So it means more covalent character, less melting point. I hope this is clear. You can write this example. And the next thing is, okay, next example is, okay, so I just want answer from your side for this particular question. So just pause the video and try this question first. Okay guys, one more thing. So you can download this PDF from NeetWorld app. So you can download this from NeetWorld app and you can use for your reference. I have written everything very nicely. You can use, or you can prepare your notes from these slides. So what is the app name? NeetWorld. You can download it from the Play Store. Okay. So once again read this question. Which of the following statement is correct? Okay. So here we have two compounds. One is FeCl3 and another one is FeCl2. So from this we have this one as, like in the both cases, chloride ion is common. Anion is common in the both case. So our answer should be like we cannot decide our answer with respect to anions. So if we see at the cations, here it is +2 charge and here it is Fe +3. Now which cation is having more positive charge? Since this is having more positive charge, it will be easily drag this negatively charged electron cloud towards itself. Therefore what happens? It will be showing more covalent nature. So what they are asking, which is more covalent? FeCl3 is more covalent than the FeCl2. So which option is correct? The first option is wrong. Second option is correct. FeCl3 is more covalent than FeCl2. Both are equally covalent. Wrong. And the next, so we cannot answer this. Next, this one also you can try first, then listen to the class. Okay. So for every question, when you are listening to a class, first of all try yourself, then later you can listen to the teacher once after trying from yourself. Okay. See, the greater covalent character of an ionic bond, if, see what they are asking, greater covalent character. See, if we take some ionic compounds, how can we decide their covalent nature? Because we know there is no 100% ionic compound. Every ionic compound will be having some covalent character. Therefore, how do we decide? Just now we discussed cation should contain small size, right? And larger size of anion, no. The next, what about this one? Also no. Then small size of anion, no. Anion should be large size, cation should be small size. So this is also no. So only option 1. Next, okay, that is about Fazan's rules. So you can solve few more questions based on that particular topic, and if you have any doubts you can ask me. Let us discuss into like one more topic here. Okay, so just give me some time. Now here we have valency bond theory. So this was developed by Hitler and London, and then next it was again further improved by who is that person? Linus Pauling. Okay, so here according to this theory, a covalent bond. So it is about covalent bond. So this covalent bond is formed between two atoms by overlapping of its half-filled valency atomic orbitals of each atom. So if we have two atoms, so we know for each atom there will be atomic orbitals. So if the atomic orbitals are half-filled or it contains some unpaired electrons, therefore the bond between these half-filled electrons of this particular atomic orbital and the another atomic orbital, bond formation takes place by overlapping of those atomic orbitals. So this concept includes what? The overlapping of atomic orbitals. Okay, So partial interpretation of interpenetration of atomic orbitals results to form a bond which we are considering it as covalent bond. Okay, so these are the postulates given by this guy, like Linus Pauling. Okay, you can read this. Okay, so now let us say we have two atoms. Let us consider we have two hydrogen atoms, atom 1 over here and atom 2 over here. Okay, let us say they are infinite, they are separated with a very long distance. Now what we are doing, these two atoms, we know in the nature hydrogen atoms will not exist, they exist as a molecule. Okay, now let us see the consider these are two hydrogen atoms. Let us bring them closer towards each other. So now what happens? See, for this atomic orbital, we know there is central nucleus. Here also we have central nucleus. Let us consider that nucleus as positive charge. Here I am writing. These are the two positive charges which represent the nucleus of two atoms. Now we have the negative electron cloud. That is what 1s1 electronic configuration we are writing now for each hydrogen atom. Okay, let us consider this negative charge indicates the electron of this hydrogen atom, and the negative charge indicates the electron of the second hydrogen atom. Now here between two oppositely charged ions there will be force of attraction, like we can consider this is a force of attraction, and here also we can consider force of attraction between the two oppositely charged charges. Now what happens between these two things? Here there is force of repulsion between the two like charges, right? This will be having force of repulsions. I am writing here, this is Fa, here also I am writing Fa, here also I am writing Fa, here also Fa, and this white color indicates force of repulsions. Okay, now when two atomic orbitals are bringing closer to each other, what happens is force of attraction is dominating and then the force of repulsions. Now see, let us consider in this graph, this is the internuclear distance, this is the distance between the two atoms, let us say, and this is the energy coordinate. Now these atoms are separated. Let us bring these two atoms closer to each other. Now see here, when we are moving from this side, it means closer towards the two atoms. The two atoms are bringing closer to each other. Now what happens? We reached a point, see, as we move this side, like the distance between the two atoms is decreasing. What happens? The energy is becoming lower, and we have reached a point, see, we have reached a point where it is having very minimal energy. It means we have reached a point where the force of attraction and force of repulsions are balanced. Now if I move further little closer, so see here, if I move this side, what happens? The two atoms are moving further more closer. What happens here? Its energy is going to the maximum. It means this is the distance where the two force of attractions and repulsions are balanced. Okay, now if you further move closer, what happens? The repulsions are dominating here. Okay, so the distance at this point where the minimal energy is observed, that minimal energy where the distance between the two atoms is having minimal energy, the minimal energy here, like this is a point where we have minimal energy. Okay, so this distance is considered as bond length. What is that? Bond length. Bond length. So what is the bond length for hydrogen molecule? So it will be 74 picometers. Okay, so now this is happened by partial overlapping. For example, this is a 1s orbital and this is a 1s orbital of two hydrogen atoms. Okay, now the partial overlapping, it means let us bring them closer. So here consider we have reached a point, so where we are looking them like this. The partial interpenetration of two atomic orbitals where it is resulting to form a bond is considered to be bond. This is a bond, and resulting molecule is considered a hydrogen molecule. Okay, the distance is 74 picometers, and this, see, the atomic orbital of this hydrogen is partially interpenetrated into the another hydrogen atom. Similarly from this side also. I hope this is clear. Okay, now see here we have seen The partial interpenetration I am saying, na, that is what called as orbital overlapping. Okay, so two atomic orbitals are overlapping, are intermixing, or we can say overlapping only for a better understanding, and results to form a molecule. Okay, the concept of orbital overlapping here. Okay, if we understand the concept of orbital overlapping little more, previously we have seen only for hydrogen. Now in order to understand for other molecule also, we must need to study for like how other atomic orbitals are also like interpenetrating or overlapping to form a bond. Okay, so here see, the partial interpenetration of atomic orbitals is called overlapping of those atomic orbitals. Okay, so these overlapping can be like just now I told now, like this overlapping means. Okay, so these overlapping of atomic orbitals can be of three types. Like it can be a positive overlapping, and it can be a negative overlapping, or it can be a zero overlapping. What exactly positive, negative, and zero overlapping? Let us see. See here, for example, here I am taking one p orbital and one more p orbital over here. Okay, we know we have how many p orbitals, like px, py, and pz orbitals are there. See, x, y, z, we know these coordinates will be perpendicular to each other like this. Okay, it means later if I say this is x axis, y axis, and z axis, these are perpendicular to each other. It means these px, py, pz are also perpendicular to each of these atomic orbitals. Now let us say I am taking two atoms which are having like p orbital over here and here. Okay, now okay, let me take this as z axis and this as x axis. Now let us consider this is pz and this is also pz atomic orbital. Okay, see, I am taking both as same axis orbitals only. Okay, now these atomic orbitals, see, what do we mean by orbital? This is a three-dimensional space around the nucleus where probability of finding electron is maximum. So let us indicate these with a positive lobe sign and negative sign. Here also positive sign and negative sign. Now the positive overlapping takes place when the orbitals with the same sign will overlap or intermix. For example, if they intermix or they overlap, we may expect to get something like this. Negative, negative. This is what the positive overlapping. See, in physics we have studied about constructive interference and destructive interference. I hope you are well aware of that. So let us say this is the wave for our understanding. Let us say like this we can take, and this is take one more wave like this. Okay, now if this positive lobe and this positive lobe are like superimposing each other, then what we will be expecting to get? So we will be getting a wave with a bigger amplitude like this. The bigger amplitude than these two waves. So we can say that is as constructive interference and destructive interference like that. No? So similarly, when we have a positive lobe interaction, or like we can say same sign lobes interaction will be resulting to form a positive overlap. If the oppositely signed lobes are intermixed or overlapped, that will be negative overlapping. And if this overlapping is not improper, like orientation of atomic orbitals are not improper. For example, I am taking px and here I am taking pz, and here if I take, instead of taking pz, if I take something like pzy, so what happens? If I take something like this, the atomic orbitals are not oriented properly, therefore it will not to form any interpenetration, or it will not undergo any overlapping to form a bond. Therefore this is considered as zero overlapping. So atomic orbitals should be oriented properly to form a bond or to overlap properly. Okay, so these are the pictorial representation from NCERT book. You can refer the same thing whatever I have discussed. See, positive signs are there. This is resulting to form positive overlapping, or we can also call it as in phase overlap. See, one s and one pz orbital which is also having positive overlapping. See here also, see here if you observe, these are oriented like this. Axially we can say both are in the same axis, so we can say axial overlap. Okay, and here this axial overlap result to form something called sigma bond. We will be discussing about that now itself, you can learn. And here it is overlapped parallelly like this, right? So parallelly means the two atomic orbitals are parallel to each other, so this results to form a pi bond over here. So this is formation of sigma bond and this will be pi bond. Similarly here, these are like oppositely charged, we can say this is negatively, like negative overlap or out of phase overlap. Okay, here also this is not pi overlap, I mean it should be from positive, and it is negative overlap. This we can say anti-bonding overlap. We will be seeing about that in the molecular orbital theory. As of now, you can consider this is positive overlap and this is negative overlap. And the next one is zero overlap. See here, one orbital is oriented like this and s orbital is in between. This is not properly oriented, right? Therefore it is considered as zero overlapping. And here see px, py, which are perpendicular to each other, I already explained. This is also zero overlapping. I hope that is also clear. The next, classification of covalent bond. So these covalent bonds are classified again based on type of overlapping. So here, if the overlapping is like along the axis, that will results to form sigma bond. See here, two s orbitals are overlapping, which are spherical in shape. Therefore, they intermix or they overlap to form like if this is a nucleus, this is the distance between the two nucleus of the atoms, we can say, and this partial interpenetration can be results to form SS overlapping, and this can be also considered as a sigma bond. Okay, so here SS overlap. See, the first bond formed between two atoms, between two like when two atomic orbitals overlap, when we consider it to be sigma bond only. Generally, this is general case. And see here, this can be results to form a sigma bond, or some other ways also there. Let us see into that. So if it is two s orbitals only, we can say this is SS overlapping. So sometimes it can be one s and one can be p orbital also. See, one sp I am taking. Sp overlapping means, see here, it is one s orbital and the one is p orbital. So now here positive sign, positive sign. So both can overlap to form a sp overlapping bond. Okay. So now in some case both can be p orbitals also. See here, I can say positive positive side and negative negative side. See here, positive positive overlapping can give us pp overlapping orbitals like this, or you can take both as negative negative also. See, both signs should be same, then the overlapping will be in phase overlapping or positive overlapping, we can say. Okay, next, see, this is about axis. See, both are like along the axis now. So both orbitals are along the axis, in the same axis, I can say, results to form a sigma bond. Okay, so sigma bond formation takes place from SS overlapping or SP, or from PP overlapping also, as of this. Okay, now here we can also get a pi bond. So how this pi bond is formed? We know p orbitals are along the px, py, pz, I mean along the three axes z, y, x, let us say. So now if these orbitals are along the z axis, now what about the remaining two orbitals? That will be along the y, and one more will be along the x axis, right? Now what about those orbitals? If this z axis orbital is overlapping to form a sigma bond, then the resulting two orbitals will be perpendicular to this axis now. See, x and y are like x, y, z are perpendicular to each other, means whatever the orbitals along those axes will be perpendicular to the other axis now. It means, see, this is z axis, we can consider this as y axis orbital, and this is also y axis orbital. These two are perpendicular to each other. Now let us say here I have a one atom and here one more atom, and this is the y axis orbital, like py orbital of this atom, and this will be for one more orbital. Now both let us bring together like this. So what happens? We will be getting an overlapping between these two orbitals, right? It means if it is positive, if it is also positive, here also if it is negative, here also it should be negative, then this will be giving a positive overlap or in phase overlapping like this. Okay, so the space between these two can be considered as nodal plane. What is that? Nodal plane. Okay, so this is how pi bond formation takes place. See, along the like parallel overlapping results to form pi bond. You should remember that. And along the axial overlapping results to form sigma bond. You can read this once again for better understanding. Okay. Then next, basically, what about strength? So we have two types of bond. One is sigma bond. I told you. See, instead of writing sigma, you can use this symbol, and you can use pi symbol like this, or you can write pi. Okay. So this sigma bond is formed by axial overlapping. Therefore, the extent of overlapping will be more in case of sigma bond. Therefore, sigma bond strength is more than the pi bond. What I am saying, sigma bond strength is more than the pi bond. You can read over here. Okay. Then next thing, we have hybridization concept, which is very important. Okay. So let us understand this hybridization concept. This is very important for your IP exams if you are 11th class, and also this is highly important for your competitive exams to understand how these molecules are forming, how the structures are given for those molecules, and valence shell electron pair repulsion theory should also be understood by every student. Okay. So here till now we have seen many concepts here. So in any of those compounds we haven't seen about how these molecules are forming, how the structures are oriented for those molecules, how the geometry are given for those molecules. So in order to understand that, we have a concept called hybridization. This is a theoretical concept. What I am saying, this is a theoretical concept. In order to understand how the geometrical shapes of polyatomic molecules like methane, ammonia and water etc. are given. For example, we are saying for methane it is tetrahedral geometry. So how it is tetrahedral? We don't know, right? So that will be explained theoretically from this concept called hybridization. Okay. So let us understand hybridization clearly. Here, so this also again introduced by Linus Pauling. Okay, according to Linus Pauling, what he is saying, atomic orbitals combine to form a new set of equivalent orbitals known as hybrid orbitals or hybridized orbitals, and the phenomenon is referred to hybridization. See, for example, okay, let us read this once again. What he is saying, then we will understand from our side. So hybridization is the process of intermixing of orbitals of slightly different energies as to redistribute their energies and resulting in the formation of new set of orbitals of equivalent energies and shape. So here, let me tell you, see, for example, carbon electronic configuration, take it as atomic number as 6. What is electronic configuration? We have 1s2, 2s2, 2p, 2p, 2. So these are 6 electrons we have. Now we know carbon has only here carbon has only 4 electrons in its valency, and it required 4 more electrons to fulfill its octet and to gain its stability, right? So for that purpose, so what are the orbital representation for this? We can represent it like this, right? So after representing it like this, now see here, we have 2s for this, and this is 2p atomic orbitals. What is this? These atomic orbitals. We know 2s and 2p atomic orbitals will be having difference in their energies. We know 2p will be having more energy than the 2s. 2p will be having more energy than the 2s. This can be explained in quantum numbers of atomic structure. That is the first chapter of your 11th. Okay, we will look into it later. As of now, you can consider this. Now here, see, hybridization is the process of intermixing of atomic orbitals slightly difference in their energy. Now, in order to form a methane molecule, what happens, you know, these atomic orbitals, see, there is some energy difference between 2s and 2p, but that is not much. So what happens is, these two atomic orbitals, which is having slightly difference in their energy, will intermix to form the hybrid orbitals. That is what I am writing here. How many orbitals are there? 1, 2, 3, 4. 4 orbitals are there now. So we have just intermixed them. Theoretical, it is a theoretical concept, we can say. So just intermix them. So now how many total orbitals are there? 4 orbitals are there. Here we are just saying it as 2s and 2p. Now here whatever I have written, you should not say it is 2s orbital, these are 3 2p orbitals. You should not say like that, because they intermix to form a new set of orbitals called hybrid orbitals. What is this called? Hybrid orbitals. So these hybrid orbitals have equal energies. What I am saying, they will be having equal energies now. So now see, redistribute their energies and resulting the formation of new set of orbitals with equivalent energies and shape. All these 4 orbitals will be having equal energies and similar shape or same shape. So now since the energies are redistributed, we need to redistribute these electrons also. How do we need to redistribute these electrons? See, we know, following the Hund's rule, what we need to do? We need to fill the 1 electron each to get maximum multiplicity. Yes, we have filled with the maximum multiplicity. Now what is the hybrid orbital's name? You should call every atom, like every hybrid orbital as, see how many are there? 1, 2, 3, 4 now. So out of this, 1 is S and 3 are P. So we can say sp3 hybrid orbital. What is the hybrid orbital's name? It should be sp3 hybrid orbital. If someone asks you what is the name of this particular orbital, you should say it as sp3 hybrid orbital only. You should not say that is s orbital. I hope this is very clear. Okay. So now after writing this, so just look here. So how many hydrogen atoms are there? 4 hydrogen atoms are there. We know each hydrogen atom is having 1s1 electronic configuration, right? So each 1s1 electronic configuration means it will be having 1 unpaired electron. Therefore, each hydrogen will be paired this electron. So whatever the 1s electron is there, 1s1 electron is there, that will be paired up with the carbon unpaired electrons. Like this, we can have 4 bonds which will be resulting to form methane molecule. And what is the orbitals hybridization? It is having hybrid orbitals sp3 now. So we already discussed that it will be having equal energies and shape. So these 4 hybrid orbitals will orient in such a way that they should experience minimum repulsions from one another. Okay, what I am saying, see, this is a bond only now. So here you should be clear with this concept first, then we can enjoy the concept, enjoy the questions. See here, I am writing the carbon at the center. So now there are 4 atomic hybrid orbitals. What is the name of those hybrid orbitals? It is sp3. So you have to represent the 4 hybrid orbitals in such a way that they should experience minimum repulsions. Why I am saying minimum repulsions? Because see, this hybrid orbital is nothing but containing 2 electrons, and this is also contains 2 electrons. In order to avoid the repulsions between these 2 electron pair, we should keep them with the maximum distance or with the maximum angle from each other. Therefore, they will be more stable. So if we see them in the 3-dimensional fashion, in the 3-dimensional orientation, it will be something like this. So you have to imagine this in the 3-dimensional view. Okay, therefore the angle here we are getting is 109.5 degrees, or you can say it is 109 degrees 28 minutes. Okay, I will tell you how to convert degrees into minutes or minutes into degrees later. Okay, as of now you can remember. So now each hybrid orbital, at the end you can write 1 hydrogen atom like this. Okay, like this. Okay, this is how hybridization takes place for this methane molecule. I hope it is very clear. Okay, so simply we can represent this in this manner: hydrogen, 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 hydrogen. So what is the angle here? Whatever I shown here, you have to write over here also. Okay, for all of these bonds, that will be constant, that is 109.5 degrees only. Okay. So how do you imagine this, or how do you see this in the 3-dimensional orientation? So I have a pictorial representation for that. See here, consider this black color carbon, black color center is carbon atom, and this, let me tell you, this, whatever the black is there, that is the central atom carbon, I have represented over here. And these yellow color lines which I have represented here, those are hydrogen atoms. See, 3 hydrogen atoms are like, if you say pyramidal shape, if you take a pyramid, see, at the 3 corners we have 3 hydrogen atoms, at the center we have carbon, and at the top we have what we have? 1 more hydrogen, right? So what is the angle over here? This is 109.5 degrees. I hope this is very clear. See, in three-dimensional view, see, this is a two-dimensional sheet, right? You can say plane. So in this plane, we have to represent a three-dimensional picture like this. This bold line which I am writing can be also called as wedge dash notation. So here it is saying thus the front side hydrogen is atom is there, no? That is what it is representing here, and back side atom is there, no? That should be represented with the dashed line like this. I hope it is very clear to everyone. So what is the angle? 109.5 degrees. Okay, I hope it is very clear. If you have any doubts, you can ask me. And the next thing is, see, we have directly went through sp3 hybridization, but before that we also have some other type of hybridization. What are those? So types of hybridization. See, in order to make you feel like better understanding, I directly went through sp3 hybridization, but before that we also have some other types of hybridization. What are those? See, in some cases we have only like two atomic orbitals are intermixing to form some molecule. Let us say two atomic orbitals as s and p atomic orbitals are intermixing. So this will be resulting to form sp hybrid orbitals, and the hybridization is called sp hybridization. So in order to avoid the repulsions, we have to keep them with a maximum angle or maximum distance, right? So two hybrid orbitals are there. So when we have two hybrid orbitals, so what is the maximum angle we can keep in the three-dimensional space? So just imagine one is this side, another one is exactly opposite side, which means that is exactly 180 degrees to each other. So we will be getting something like this. What is the angle here? We are getting 180 degrees. So for this kind of hybridization, we have BeCl2 as an example. So what is the atomic number for beryllium? Beryllium is 4. So we can write 1s2, 2s2. And we already discussed in bond formation only valence electrons will be involved. Therefore, here how many electrons are there? 2s, 2 electrons are there. Next, what is the orbital we have? 2p0 we have. So in order to explain what is the exact geometry of or structure of this molecule, we have to use this hybridization concept. We can write 2s like this and 2p like this, 0, 2s to 2p 0. Now we can excite the 1s electron from 2s electron from here to here, or we can intermix them. Therefore we are getting something like this here and here. Therefore here we have one sigma bond with the chlorine atom, another sigma bond with the chlorine atom. Therefore how much what is the orbitals we have here? Hybrid orbitals we have, one is s and another one is p. Here we have s and p, so we can say sp hybridized. So what is the orbital angle here? 180 degrees, and this is the beryllium center. So you can say this is one chlorine atom, and here one more chlorine atom you can consider. So this should be like chlorine atom p orbital, here also chlorine atom p orbital. I hope this is very clear. If you want, you can see this example. So this is a pictorial representation of BeCl2. Okay, then next we have, similar to this, we have sp2 hybridization and sp3 we already discussed, then sp3d and the next sp3d2 hybridization, etc. like that. Okay, so let us see one by one. So now we have finished about sp2. Let us discuss about we have discussed about sp and sp3. Now see, this is about sp hybridization. Now let us say BeCl3 as an example. So here what is the boron electronic configuration? It is 1s1, 1s2, 2s2, 2p1. So we have to consider only valence electronic configuration. You can write it as like this, right? So after writing this, see how many surrounding atoms are there? 3 surrounding atoms are there. In order to make a bond, we should have one unpaired electron or half-filled atomic orbitals to pair up with this chlorine. So to make that, so we can excite the electron from here to here, and the hybridized orbitals are 1, 2, 3. So now here each 3 unpaired electrons are there. Each one can form a bond with each chlorine. So what is hybridization we are getting? one s orbital, I mean sp, like sp2. So totally it will be sp2 hybrid orbitals. How many sp2 hybrid orbitals are there? There are 3 sp2 hybrid orbitals. So here if you see, in the first case, here it is sp hybridized. I told you, here I have explained, this is sp hybridized. What is the percentage of s and what is the percentage of p if they ask? See, there are only two orbitals are there. One is s, another one will be p. It means s will be having some 50% and p will be having some 50%. Totally it will be 100%. Similarly, when it comes to this sp2, what is the percentage of s and what is the percentage of p, they may ask. So it will be, this will be having 33.33% you can say, and this will be 66.66% you can say, or 67% you can say. Okay, now these p3, how many hybrid orbitals are there? There are 3 hybrid orbitals are there. Now how do we orient these 3 orbitals, hybrid orbitals in 3-dimensional space? See, we can keep these 3 hybrid orbitals in 3-dimensional space in this way, like in a plane you can keep with 120 degrees of angle. So what is the angle here? 120 degrees. Central you can consider boron atom. With each corner you can consider 3 chlorine atoms over here. Okay. So what is the angle between the each bond? Between 2 bonds? It is 120 degrees. I hope it is clear. So now this particular shape is called linear shape. What is that? Linear. Now what about this? This will be called as trigonal. See, three bonds are there, no? So we can say trigonal planar, and complete molecule is lying in a plane now, so we can say trigonal planar. I hope this is clear. Okay, so now in some cases what happens, here we have surrounding 3 atoms are there. Sometimes for some molecules we will be getting sp2 hybridization only, but there are only 2 surrounding atoms. One example for that is SO2. So in this case what happens? See, here we have surrounding 3 atoms are there. But what I am saying, in few cases, like see SO2 I am writing now. So in the SO2 case if you observe, surrounding how many atoms are there? Only 2 atoms are there. In that case, one hybrid orbital should be having no atoms, it will be having only electrons. In that case, how do we decide what is the angle here, what is the shape? So that will be clearly we can study in valence shell electron pair repulsion theory, that is in the next class. And see, you should not miss this class before going to that, because these are very basic concepts which will be highly helpful for that. If you watch these 2 videos, it will be highly helpful and you can able to solve at least 1 or 2 questions. See, from these 2 videos which I am going to do now, this one and the next video, definitely you are going to see 1 or 2 questions, definite for sure. So you can easily score from those 2 questions if you watch this. Okay, here I have explained sp3 hybridization also by taking methane molecule. Now what is the percentage of S here and what is the percentage of P in sp3 hybridization? See, this is sp3 hybridization we are saying now. So what is the percentage of S and what is the percentage of P? I just wanted to know from your side. Okay, so total how many orbitals are there? See, sp3 means 1 is S and 3 are P, so total 4. So total 4 means, so percentage of S I am asking, so how many S orbitals are there? 1 by total 4 into 100, you can say this is 25% S, and what is the remaining? That will be 100 minus 25, we will be getting 75% P character. Okay, so here also, see here there are total 4 atoms around the carbon, right? So in some cases what happens, one atom will be missing, but here we may have some lone pair electrons. Now the shape of the molecule is changed. So here it is tetrahedral, now it is becoming pyramidal shape. See, just remove this or just remove this. What is the shape? We can say this is like a pyramid now, like a pyramid. See, this is a pyramid now. So in that case, how do we what happens to its bond angle and how it will be varies from here to here? We are going to learn that thing in the next class. Okay, so here again, see, from here I have removed only one atom. So in the second case, I can also remove both atoms. I can replace them with the lone pair electrons. Therefore, we are getting something like this. This is an example of like H2O molecule which is having a bent shape. So what is the angle over here that we are going to learn in the next class? Okay. Okay. So what about this particular structure? So this will be, see, till now we have discussed sp, sp2, sp3. Then next it should be sp3d. So what exactly sp3d hybridization? So here let us say PCl5. Okay, in this what is the central atom? We have phosphorus. What is the electronic configuration? Valency 3s2 3p3. Therefore 5 valency electrons are there. We can represent like this. Now after 3s 3p we have one more 3d 0. So why I am writing this 3d 0 here? See, this is the next atomic orbital now for this phosphorus atom. See here how many chlorine atoms are there? 5 monovalent atoms are there. Therefore, we require 5 unpaired electrons to pair up with each of this chlorine. Therefore, we have to take this empty d orbital also. So, if you take this empty d orbital, see here we have like this. Now, we can excite this electron from here to here. Therefore, we are getting like this. So if we observe here 1 Cl, 1 Cl, 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 Cl. So this is the hybrid orbitals which are involved. So what are the hybrid orbitals involved? So one is S and 3p orbitals and 1 d. So we can say all these should be called as sp3 orbital, sp3d hybrid orbitals. Okay, like this. Now how many hybrid orbitals are there in total? We have 5 hybrid orbitals. These 5 hybrid orbitals you have to place in such a way that they should experience minimal repulsions again. So in order to do that, so you just keep 3 hybrid orbitals in a trigonal planar manner first for better understanding. So this should be trigonal planar. Okay, like a triangle you can say. So in the triangle you just like take from the center to the each corner. Now you take one more line above side and one more below side. So total 5 bonds are there like this. Okay, so here how many chlorine atoms are there total? In total we have 5 chlorines. So you can keep here like this. Okay, so now what is the angle here? It is, see, in a triangle what is the angle we have? Internal 120 degrees. Now what about this angle? See, this is a plane. On the above the plane we have one. See, this is how you should look in the 3-dimensional view. See, these are the three orbitals like a triangle, and we have one is above the triangle and one is below the triangle. So it means it should be 90 degrees. So here it is 120, here it is 90. Now you have to remember that this trigonal planar like lines whatever we have written with yellow color, that you should call it as equatorial bonds. Equatorial bonds. And the remaining the white color lines above and below can be called as axial bonds. So here you have to remember that equatorial bonds will be having relatively equatorial bonds are more stable than the axial bonds. Which are more stable? Equatorial bonds are more stable than the axial bonds. Okay, and see, now the S and P character, like S character is more oriented in the equatorial bonds. See, there are 2 types of bonds in the PCl5. What are those? One is equatorial, another one is axial. So now in which bond more S character is oriented? So you have to answer this as S character is more oriented in the equatorial bonds because it is having maximum angle. So in that way you can answer this. And which are more stable, like which are relatively more stable, I am saying equatorial bonds are more stable than the axial. That's why if you look into this, PCl5 upon heating decomposes as PCl3 plus Cl2, right? So it means 2 weaker bonds. Whatever these 2 axial bonds are there, they are relatively weaker. Therefore, they will be dissociate and will be having PCl3 and Cl2 as a compound, as a products. Okay, I hope this is also clear. We will learn about this in detail in the upcoming class, that is after discussing valence shell electron pair repulsion theory, because we may expect question from this sp3d geometry or any of the other concept. And this is the sp3d hybridization pictorial representation. And then next we have SF6 is an example for, see how many hybrid orbitals are required here, sp3d2. We are discussing about sp3d2. So for this I am taking SF6 an example. See, sulfur has, what is the electronic configuration? A valence electronic configuration 3s2 3p4. This is the sulfur element from the oxygen family. So you can say 3s2 3p6 3p4, and you can write it like this, And next thing is we have 3d0. Why I am taking 3d0? Because we require 6 bonds, because 6 monovalent fluoride ions, like fluorine atoms are there. Therefore 6 bonds are required. So in order to form 6 bonds, we have to make the 6 available orbitals, hybrid orbitals. So in order to do that, we can excite one electron from here to here, right? Therefore we are getting it as so from here to here we have excited. So you can call it as first excited state. What is that? First excited state. Similarly, see how many orbitals are now, how many electrons are available now? 1, 2, 3, 4. But we require 6 bonds to make the molecule. Now we can we have one more chance to excite the electron from the s orbital to d orbital. So for this, from here to here we can do. Therefore we can get like this. Okay, so now check how many hybrid orbitals are there. See, we have 6 hybrid orbitals to make 6 monovalent, like 6 bonds with fluorine. So how many orbitals are involved here? 1 s orbital and 3 p orbitals and 2 d orbitals. So what is the name of this hybrid orbitals? You should call sp3d2. So sp3d2 orbitals will be oriented in this manner. So if you consider a plane like a square, you can say, so in the square you can just keep 4 atoms. In a square you can keep 4 atoms like this. So on the above the square you can keep one more bond, like one more atom here, and the below the square you can keep one more atom. So what are the orbitals, like atoms lying in the square, I mean in a plane? You can consider it as a square for understanding. So those atoms and the central atom will lie in the plane, in one plane, in the square I am saying, and above and below atoms will lie above the plane and below the plane. So how many atoms are within the plane? You have to say that is 5 atoms are within the plane and 2 are out of plane, you can say. Okay, I hope this is also clear. So what is the angles now? See, between these between any of the 2 atoms, if we say, see between these 2 atoms if we consider, that is also 90 degrees. See, in a square if we take between any of these 2 lines, what is the angle? But between any of these 2 lines, so what is the angle we can say? That is 90 degrees now. Okay, so between any of these adjacent one, 90 degrees. And what about this one, which is having like this, which is having like this or like this or like this, like it is like this now. So what is the angle? What is the angle between this line? This is 180. What about this angle? This is 90. So like that we have 90 and 180 degree angles. So my question is, how many 90 degrees angles? How many 90 degrees and 180 degree angles are in SF6 molecule. This you have to answer in the comment box. And one more question I just wanted to give you is, in PCl5, how many in PCL5, here you can say in PCL5, how many 90 degrees and 120 degree angles are present. So these are the PYQ questions in some, I think in JEE mains. So you have to answer these kind of questions just by observing these particular geometries. I hope the concepts are very clear. If you have any doubts regarding our discussion, you can tell me in the comment section, or you can directly contact us from the provided mobile number in the description box, and you can access this complete PDF in the NeetWorld app. Thank you once again for watching this video. Okay, nice to meet you.